We have a cylindrical can with a closed top, and it will have a capacity of 56 pi inches cubed, so that's the volume. We have the cost of the materials used for the top and the bottom are 20 cents per square inch, and the cost of the material for the curved parts of the sides is 25 cents per square inch. And we want to find the dimensions. Those are going to be radius and height because the base is a circle. That will minimize the cost of the material, so cost, and we want to find the minimum cost. So what do we know? We know a lot of things about this cylindrical can. So let me draw a diagram. Cylinder. So we have a cylindrical can. And the important things about a cylinder are the radius and the height. So we happen to know the volume, and ultimately we're going to write a cost function. That's the thing we want to minimize. Let's start with the volume because it's easy to do. So volume is given as 56 pi inches cubed, and the volume is calculated for a cylinder. You'd take the area of the base and you multiply it by the height. So the area of a circle is pi r squared. So it would be pi r squared times the height, which is h. So that's the volume. And now let's write an equation for cost. So the cost. All right, let's do it one piece at a time. So the cost for the top and bottom is 20 cents per square inch. So the top and the bottom. So those are the two circles. So we have two circles. So I'm going to multiply the area of the circles by 2. And the area of a circle is pi r squared. So 2 times pi r squared. And then the cost for those, so that's the area of them, is 20 cents per square inch. So I'm going to multiply that by 0.20, 20 cents per square inch. And then I need to find the cost for the lateral side. So this curved area here, which is a rectangle. If you slice this down the side and flattened it out, the width of the rectangle would be the area, the circumference of the circle, and the height would be the height. Okay, so that rectangle is 2 pi r, circumference of the circle, times the height. And then that area costs 25 cents per square inch. So we're going to multiply by 0.25. So that's the cost function. But we have too many variables. We have r's and we have h's. So I need to solve my volume equation for one of the variables and substitute so that I have only one variable. So to me, it seems easiest to solve this for height because then I don't have to take a square root. So if I solve this for height, I would divide by pi r squared. So I would have 56 pi divided by pi r squared, and that would equal height. I divided both sides by pi r squared. So that tells me that height, and cancel the pi's, is 56 over r squared. So let's write our cost function in one variable. So 2 pi, actually, let's multiply at the same time. So 2 times 0.2 is 0.4 pi r squared. And then 2 times 0.25 is 0.5 pi r. And then height is 56 over r squared. So we will simplify a little bit. So this term doesn't really simplify, but this one does. R divided by r squared leaves me with 1 r in the denominator, and 0.5 times 56 is 28. So that leaves me with 28 pi over r. And because I want to take the derivative, and at this point, I'm going to write c as a function of r. And I'll rewrite this with the r in the numerator for ease of taking the derivative. Didn't change the first term. 28 pi r to the negative 1. And let's stop now that we have a function for the cost and state the domain. So the radius obviously has to be bigger than 0 or we don't get a circle down here. And the height could be really tiny, making the radius really big. So that's all we know about it. So the radius has to be greater than but not equal to 0. So this is not a closed interval. We're going to have to check at the end and find out if we really found a minimum. So now let's take the derivative, bring down the 2. So 2 times 0.4 is 0.8. Keep the pi, that's a coefficient. R to the 1, I don't need to write the 1. Bring down the negative 1, so that's negative 28. Keep the pi, that's a coefficient. Decrease the exponent by 1, so that exponent is negative 2. Now we want to find the critical value, so we'll set this equal to 0. And I will first rewrite this with only positive exponents. So the r squared is going to move into the denominator. I would really like it if I didn't have an r squared or any r in the denominator. So I will multiply the entire equation by r squared. That will give me 0.8 pi r cubed, right? R squared times r. And then r squared divided by r squared, that's going to cancel and leave me with 28 pi. 0 times r squared is 0. When you do this and multiply by a variable and a 0 on the other side, you might gain extraneous solutions because you kind of had an extra variable show up in there. But we check for those anyway. So now, relatively simple, 0.8 pi r cubed. I'm going to add 28 pi to both sides. And then I will divide by 0.8 pi. And that gives me r cubed equals 28 divided by 0.8, which is 35. I did that in the calculator. And then we want to take the cube root of both sides. So that gives us r equals, again, calculator problem, 3.27. So that's our only critical value. And we don't have boundaries on the top of the domain and our lower boundary is not included. So my really boring table is only going to have one value in it. So I said X, but it's actually R radius. And again, we're plugging it into the cost function. We're not plugging it into the derivative. So this is strictly cost. And what we're plugging in is our one critical value, 3.27. And calculator problem, type that in, and we get 40.34. And we're hoping that's a minimum cost. But because we don't have a closed interval, we need to check in some way. Two of our possible ways to check are to do sign graph analysis on the first derivative, or we can use the second derivative test. So let's do the second derivative test. So first we have to take the second derivative. So here's our first derivative. So all of this is a coefficient times a variable. So that becomes just the coefficient. So 0.8 pi, no r. And then negative 2 times negative 28 is positive 56. and I still have the pi, and I decrease the exponent by 1, so that would be r to the negative third. And we did this so that we could plug in our critical value, 3.27. And I plug that in to the second derivative. I did this in the calculator, and I get 7.54. But the point of this is it positive or negative? So that's positive. That means it's concave up. Therefore, that critical value is a minimum, which is great because that's what we wanted. Minimum. That was hard to read, but minimum. So we had a minimum. Great. That's what we wanted. So now let's state our answer. So the minimum cost is $40.34 for the materials to make this can. And it occurs when, and we need the dimensions, the radius is 3.27 inches. And we also need the height. So how do we find the height? So we have an equation up here, simple one, where the height is 56 divided by the radius squared. So we plug in 3.27 there, and we find out that the height is 5.24 inches.